Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the DC ammeter. Our objective is to introduce the DC ammeter function on the digital multimeter and use this feature to measure current in an electrical circuit. Additionally, I'm going to show you how to replace a blown fuse in an ammeter, not if, but rather when your lazy lab partner damages one because of improper use. This lecture operates under the presumption the viewer has watched both the ohmmeter and the DC voltmeter lectures available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. For the purposes of today's lecture, we'll be making use of the BK Precision 2831E digital multimeter. This in no way is meant to be neither an exhaustive review of this tool nor an endorsement of this particular manufacturer or model. I only wish to present the function of interest on a representative example so the viewer can gain some practical exposure to this function and interpret the manner in which results are displayed. A digital multimeter, or DMM, is a single meter that has multiple, hence the term multi-mode settings. DMMs can be used to measure both DC and AC voltage and current, resistance, capacitance, forward bias voltage of a diode, frequency, and much more. Today we're only going to look at the DC ammeter function on the BK Precision 2831E DMM, where a DC ammeter is a device used to measure the DC current traveling through a closed electrical circuit. We'll examine other functions of this DMM in later lectures. Bottom line up front, ammeters aren't easy to use at first because they necessitate modification of the circuit under inspection. Ammeters measure current through a device and must be placed in series or in line with the device under inspection. To become adept at the use of an ammeter necessitates guidance, practice, repetition, and a couple firm strikes across the back of your hand with a wooden ruler when you screw it up. If you recall, current is an important basic electrical property. Current is a measurement of moving charges, where 1 amp of current is 1 coulomb of charges per 1 second. Voltage, in contrast, is a measurement of how much energy possessed by a group of charges, where 1 volt is 1 joule of energy per coulomb of charge. This implies that voltage and current are not the same thing, and they are not measured in the same manner. At a basic level, current is a flow rate measurement of particles moving past a single point per unit time. To properly measure current, all flow must pass through the ammeter. This necessitates modification of the circuit under inspection, oftentimes a challenging task, even in the best of circumstances. Consider an 8-volt source supplying current to a 100 ohm resistor. An application of Ohm's law demonstrates 80 milliamperes of current would travel clockwise through this circuit. For us to properly measure current would necessitate we insert an ammeter inside the circuit such that all flow passes through the ammeter. We need to break this circuit and insert an ammeter. There's a couple ways of doing this. First, it's a recommended safety practice to turn off the power supply before breaking the circuit. Failing to do so might cause a dangerous arc to form at the break. Although this is a relatively low power application, it's always good to start safe work practices now. Here the circuit is broken between the positive terminal of the 8-volt source and the top terminal of the 200 ohm resistor. An ammeter can then be inserted into this system such that conventional current leaves the positive terminal of the 8-volt source, enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, enters the resistor top terminal, travels through the resistor, leaves the resistor bottom terminal, and returns to the negative terminal of the 8-volt source. One and only one path for current exists, such that the ammeter is part of the circuit and all conventional current will travel through it for measurement purposes. When the source is turned back on, an ammeter configured in this fashion would read 80 milliamperes. Customarily, the red lead is considered the indoor of the ammeter, and the black lead is considered the outdoor of the ammeter. Here's another equally effective manner in which to measure current in this circuit. Here the circuit is broken between the bottom terminal of the resistor and the negative terminal of the source. An ammeter can then be inserted into the system such that conventional current leaves the positive terminal of the 8-volt source, enters the resistor top terminal, travels through the resistor, leaves the resistor bottom terminal, enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, and returns to the negative terminal of the source. One and only one path for current exists, such that the ammeter is part of the circuit and all current will flow through it for measurement purposes. When the source is turned back on, an ammeter configured in this fashion would also read 80 milliamperes. In both scenarios, the ammeter is a single point in line or in series with the element of interest. An ideal ammeter acts like a 0 ohm resistor through which substantial current will flow and the presence of which will not influence the circuit in any way, shape, or form. In reality, an ammeter doesn't really have 0 ohms of resistance, but rather an extremely small resistance and will subtly influence the circuit under inspection. For now, Let's simply assume an ideal scenario in which an ammeter acts like a 0 ohm resistance through which substantial current will flow, and the presence of which does not affect the circuit. We'll examine instrument loading effects in later lectures on series parallel DC circuits. Let's place a DMM in DC ammeter mode to measure current in a real-world circuit. To do so, we need to use the checklist. I'm not urging you to use this checklist every time. I'm demanding you use this checklist every time. This checklist will save your measurement equipment and circuit a lot of costly downtime and may potentially save your life. I am not overstating the benefits of using this checklist. Use the checklist. Think about it. Really think about it. Take your time and think before you act. The checklist has 4 steps. Follow them 1 through 4 and you will get it right every single time. Skip a step, do a step wrong, or do a step out of order and you will get it wrong every single time. Function, leads, range, placement. Function. We need to place the DMM in DC ammeter mode. Upon powering up the BK Precision 2831E, we see it does a quick functions check and immediately defaults to the DC voltmeter function. Place the DMM in DC ammeter mode by pressing the light blue shift key, which activates the secondary functions written in light blue above the primary keys. Then select DCI for DC ammeter in the upper left-hand corner. Leads. Before we make use of the DC ammeter function, we need to insert the leads in the right place. Black lead into the black common hole. This is the outdoor of the ammeter. There are 2 choices for the indoor. One, an indoor reserved for measurement of large amounts of current up to 20 amperes. Another indoor reserved for measurement of small amounts of current up to 200 milliamperes for DC and up to 500 milliamperes for AC. Since our anticipated current draw is 80 milliamperes, we clearly don't need to resort to the high current input, and the low current input should work just fine. Of note, a DMM in DC ammeter mode uses different inputs than it would an ohmmeter or voltmeter. I say again, an ammeter uses different inputs. This is where attention to detail is of paramount importance. An ammeter uses different circuitry to measure current, and if deployed incorrectly, you can damage the meter, the circuit, or yourself. Pay attention when you use an ammeter. It is not a voltmeter, it's an ammeter, and it uses different lead placement. Range. Ordinarily, I'd say don't worry about it because the BK Precision 2831E is auto-ranging. However, I must caution you that there are 2 inputs for the ammeter function. One intended for high current up to 20 amps, and one intended for low current up to 200 milliamperes DC and 500 milliamperes AC. Inside the low current input, it is auto-ranging. However, one must manually select the high current input range. We'll explore the high current measurement scale in a moment. For now, let's just use the auto-ranging low current input. Finally, placement. The circuit must be broken and an ammeter inserted inside the circuit such that all flow passes through the ammeter. Ammeters must be placed in series or in line with the elements through which current is to be measured. This is perhaps the most difficult concept for individuals unfamiliar with ammeters to comprehend. Current measurements necessitate invasive insertion of the ammeter in series, and the circuit must be modified to accommodate this change. Consider the simple electrical circuit consisting of an 8-volt source positive terminal and one terminal of the 100 ohm resistor landed on node 5A through E, and the other terminal of the 100 ohm resistor and source negative terminal landed on the node 5F through J across the ditch. A complete electrical circuit exists such that one and only one path where current exists through the 100 ohm resistor. Upon powering up the power supply, we see the analog current meter needle jump to some indiscernible hash mark around the 80 milliampere range. This seems correct. However, a DMM in DC ammeter mode could make a far more accurate measurement of current. Importantly, one cannot insert an ammeter into this circuit without modifying it. Power off the power supply. Break the circuit such that the 8-volt source positive terminal is no longer landed at node 5A through E, but rather dangling out in space. This is an open circuit and no path exists through the resistor. Now, we need to insert the ammeter to bridge the open such that all current must pass through it. Out of the power supply positive terminal, into the ammeter indoor. Through the ammeter. Out of the ammeter outdoor, into the resistor at node 5A through E, through the resistor, out of the resistor at node 5F through J, and into the power supply negative terminal. A complete circuit has been established and all current will pass through the ammeter. When we power on the power supply, the ammeter displays a far more accurate measurement of current consistent with our theoretical calculations. This isn't the only place one can measure current through this circuit, and other options exist. Consider the original unbroken circuit with a power supply positive terminal and one terminal of the resistor landed at node 5A through E, and the other terminal of the resistor and power supply negative terminal both landed at node 5F through J across the ditch. A complete electrical circuit exists such that one and only one path for current exists through the resistor. Power off the power supply. Break the circuit such that the 8-volt source negative terminal is no longer landed at node 5F through J, but rather dangling out in space. This is an open circuit and no path exists through the resistor. Now insert the ammeter to bridge the open such that all current must pass through it. Out of the power supply positive terminal into the resistor at node 5A through E, through the resistor. Out of the resistor at node 5F through J, into the ammeter indoor, through the ammeter, out of the ammeter outdoor, and into the power supply negative terminal. A complete circuit has been established and all current will pass through the ammeter. As previously, when we power on the power supply, the ammeter displays a far more accurate measurement of current consistent with our theoretical calculations. Note that the ammeter assumes conventional current travels from the positive terminal of the source to the negative terminal of the source, i.e. in the indoor and out the outdoor. If one was to power down the source and swap the indoor and the outdoor, such that 80 milliamperes of conventional current was coming in the outdoor and out the indoor, the ammeter will recognize this reversal of flow and signify it using a negative sign. When we power on the power supply, the ammeter displays roughly negative 80 milliamperes of current consistent with our expectations. Let's now discuss how to make use of the high current input. Given we're well below the upper limit of the low current input, the low current input is the best choice. However, if your expected current is ever above the upper limit of the lower current input, you'll need to make use of the high current input. First, before making any modifications in your circuit, power off the power supply. The BK Precision 2831E DMM is auto-ranging inside the low current input. However, it must be manually placed into the higher range. To make use of the high current input, insert the lead intending to be the indoor of the ammeter inside the 20 amp input. Then, manually change the range by pressing the up level key until you arrive at one of two options, either 2 amps or 20 amps. Let's use the 2 amp range. Given our expected current is much smaller than 2 amps, we'll still read current, but this input might not give us the most accurate results. As previously, break the circuit such that the 8-volt source positive terminal is no longer landed at node 5A through E, but rather dangling out in space. This is an open circuit and no path exists through the resistor. Now insert the ammeter to bridge the open such that all current will pass through it. Out of the power supply positive terminal, into the ammeter indoor, through the ammeter, out of the ammeter outdoor, into the resistor at node 5A through E, through the resistor, out of the resistor at node 5F through J, and into the power supply negative terminal. A complete circuit has been established and all current must pass through the ammeter. When we power on the power supply, the ammeter displays a reasonable, yet less accurate measurement of current, still consistent with our theoretical calculations. Again, the BK Precision 2831E is auto-ranging inside the low current input, however it must be manually placed into the higher range. If the high current input isn't reading current, chances are you haven't told the DMM you want to make use of the high current input by manually ranging it. Alright, that was easy, wasn't it? No. First-timers traditionally struggle with ammeters because they simply fail to recognize that the circuit must be broken first and the ammeter inserted inside the open such that all current must pass through the ammeter. Additionally, first-timers often fail to recognize that ammeters use different lead placements than voltmeters. As a solution to this problem, I suggest you use the checklist. Function, leads, range, placement. If you follow the checklist in its intended order, you cannot get it wrong. If you skip a step, do a step wrong, or do a step out of order, you will get it wrong. In summary, use the checklist. You'll be glad you did. Since proper placement of the ammeters seems to be the skill that eludes most first-timers, allow me to spend some more time hammering this subject. By all means, draw a picture and talk yourself through it. Think how conventional current flows through the circuit. Current leaves the positive terminal of the 8-volt source, enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, enters the resistor top terminal, travels through the resistor, leaves the resistor bottom terminal, and returns to the negative terminal of the source. One and only one path where current exists, such that the ammeter is part of the circuit and all current must travel through it for measurement purposes. Build the circuit exactly as illustrated, step by step, and make sure one and only one path where current exists. Take your time and think about it. Really think about it. Draw a picture and talk yourself through it. In this spirit, because the ammeter is a little tricky to use at first, here's a couple ways you might screw it up. Be on the lookout for these mix-ups and be smart enough to recognize them when they happen. Here's one way of taking a bad current measurement. Recall that ammeters use different lead placements than voltmeters. What if you landed the lead intending to be the indoor, not on the proper ammeter input, but rather on the voltmeter input? No current would travel through the ammeter portion of the DMM, and an ammeter configured in this fashion would measure no current. Given ideal voltmeters are modeled as infinite resistances through which no current will flow, current will not travel through the circuit. Here's another way of taking a bad current measurement. The circuit must be broken and the ammeter must be placed in series with the element of interest. What if you put the leads in the right place, but failed to break the circuit and attach the indoor and the outdoor of the ammeter to the same node? Consider both leads of the ammeter landed at node 5A through E. No current would travel through this ammeter. However, current would continue to travel inside the unbroken circuit. An ammeter configured in this fashion measures no current. All current bypasses the incorrectly configured ammeter. Here's yet another way of taking a bad current measurement. Again, the circuit must be broken and the ammeter must be placed in series with the element of interest. What if you failed to break the circuit and landed the indoor and the outdoor of the ammeter in parallel with the element of interest? Pay attention, because this is perhaps the most egregious of errors, and regrettably, the most common of errors for individuals unaccustomed to ammeters. Be warned, this is wrong and extremely dangerous. Placement of an ammeter in parallel with an element of interest can have disastrous consequences. Recall that ideal ammeters are modeled as 0 ohm resistances through which substantial current can flow. Additionally, recall that the resistance of a parallel configuration of elements is always smaller than the smallest resistor constituting the parallel relationship, and additionally, that 0 ohm shorts inside parallel configurations effectively short out the entire parallel configuration. An ammeter configured in this fashion will present no opposition to the source, and substantial, theoretically infinite amounts of current can flow. This could damage your meter, your circuit, or yourself. Never, ever put an ammeter in parallel. For the curious, let's do so in a controlled environment. Here I've current limited this DC power supply to a maximum of 125 milliamperes, meaning if the circuit draws more than the user-adjusted maximum of 125 milliamperes, the source will actively reduce its voltage output to keep current under the permitted maximum. In addition to actively attenuating or reducing output, the current limited source will throw a red flag in the play and let us know we're pegging the maximum by illuminating the overload LED. For a detailed discussion on current limitation, check out the DC Power Supplies lecture available at the Big Bad Tech channel. Long story short, the source actively reduces voltage output such the current remains below the user-adjusted maximum, in this case 125 milliamperes. Consider the original unbroken circuit, the power supply positive terminal and one terminal of the resistor landed at node 5A through E, and the other terminal of the resistor and power supply negative terminal landed on node F through J across the ditch. A complete electrical circuit exists such that one and only one path of current exists through the resistor. If we failed to break the circuit and place the ammeter in parallel with the resistor by landing the indoor at node 5A through E and the outdoor at node 5F through J across the ditch, another parallel path in this circuit exists through the ammeter. Notably, this parallel path presents no opposition to the source and substantial current will flow. Again, this is not how you use an ammeter, and seriously bad things will happen. Never ever place an ammeter in parallel. When we turn on the power supply, an ammeter configured in this fashion demonstrates 125 milliamperes, our permitted maximum flows through the ammeter. Additionally, the source indicates it's in an overload condition by illuminating the overload LED. If this light illuminates, it means you're doing one of the following. 1. The user adjustable current limit is set too low. 2. There's a short circuit. Or 3. You're using the ammeter incorrectly. Either of these scenarios may cause your lab instructor to swoop down upon you like a hungry peregrine falcon would swoop down upon a wounded pigeon. Make sure you're not there when this happens. Just let your lazy lab partner absorb the wrath. Keep in mind this is in a controlled lab setting with a current limited source. If we made the same mistake on a source that could produce a maximum of, let's say, 100 amperes of current, all 100 amperes would be diverted through the ammeter. This is a sure way to destroy this device and those in close proximity. It is for this reason ammeters incorporate safety fuses on their inputs. A first defense is to deploy the ammeter properly by using the function, leads, range, and placement checklist. If you use the ammeter properly, this won't ever happen. As a backup defense, the fuse is there to rupture in the event you screw it up. Fuses are inexpensive, sacrificial elements designed to blow before anything else more expensive does. The low current input on the BK Precision 2831E has a 1 amp fused input, meaning it'll handle, but not necessarily read, anything up to 1 amp. Beyond 1 amp, the fuse element melts and breaks the circuit, saving the ammeter from certain destruction. Similarly, the high current input on the BK Precision 2831E has a 20 amp fused input, meaning it'll handle anything up to 20 amps. Beyond 20 amps, fuse element melts and breaks the circuit, saving the ammeter from a fiery end. When a fuse blows, that input is rendered inoperable until the damaged fuse is removed and a suitable replacement is inserted. Now I know you're smart enough not to damage your ammeter, but look around your lab. Do you trust any of them? My point exactly. Oftentimes in a communal lab setting where several groups of students share the same equipment, it's the previous lab group that has damaged the equipment and left it as an unwelcome surprise for the following group. If your ammeter isn't reading current and your inspection detects no other obvious opens, most likely the fuse for that particular input is blown. In this spirit, here's a quick guide how to test and replace fuses. First, an ideal fuse in the intact and functional state will present 0 ohms of resistance. Real fuses may exhibit a small, negligible amount of resistance. Here, an ohmmeter demonstrates that this fuse is intact and functional. A blown fuse, in contrast, is an open and presents infinite resistance. Here, an ohmmeter demonstrates that this fuse is blown and inoperable. This is a sure sign that someone's been using this ammeter incorrectly. Replacing the low current input fuse in the BK Precision 2831E is super easy. Unplug the DMM, remove the leads, and locate the fuse carrier on the front panel. Use a screwdriver to rotate the fuse carrier several turns counterclockwise. Take the fuse and fuse carrier out of the socket. Remove the damaged fuse and replace it with an intact fuse of exactly the same type. Reinsert the fuse carrier and carry on with your mission. Replacing the high current input fuse in the BK Precision 2831E necessitates a little more work. Unplug the DMM, remove the leads, and turn it around to the back. Pull the bumper off the back and locate the 2 screws holding the trim on. Unscrew the screws and remove the trim. Then slide the case off. The high current input fuse is located behind the front panel on the left when looking from the back. Pop out the damaged fuse and replace it with an intact fuse of exactly the same type. Reassemble and carry on with your mission. Alright, I do believe that's it for now. Again, let me remind you that an ammeter is not a voltmeter and it is not used in the same fashion. Not only do ammeters make use of different lead placement, an ammeter must be placed in series with the element under inspection, and this necessitates modification of the circuit under inspection. Power off the power supply. Break the circuit. Insert the ammeter. By all means, draw a picture and talk yourself through it. Think how conventional current flows through a circuit. Current leaves the positive terminal of the source, enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, enters the resistor, travels through the resistor, leaves the resistor, and returns to the negative terminal of the source. One and only one path where current exists, such that the ammeter is part of the circuit and all current will travel through it for measurement purposes. Build the circuit exactly as illustrated, step by step, and make sure one and only one path where current exists. Take your time and think about it. Really think about it. In conclusion, this lecture introduced the DC ammeter function on the DMM. We use the function, leads, range, and placement checklist to place the DMM in DC ammeter mode and use the DC ammeter to measure current through an element inside a closed electrical circuit. Additionally, we discussed steps to prevent incorrect use of DC ammeters. Finally, we learned how to replace a damaged fuse inside an ammeter. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.